So first I would like to thank all the organizers for the nice invitation here. This work I'm about to present is a collaboration with Lars Andersson from the AI and Thomas Begdel from the Maxwell Institute in Edinburgh. The last version of the thing can be found here. You have a previous version. So now I think it's online. I don't know, I'm not sure. It is. So, and previous version on the archive is here. So this work here, does it work now? Yes. Yes. So this work here is, again, always in the spirit of understanding the nonlinear stability of Kerr black holes. Especially under the aspect, as we have already many times discussed here, the higher spin fields. We know from the result of the Minkowski stability that the higher spin field was an important thing that has to be understood as a preliminary result on flat spacetime. The asymptotic behavior of this field had to be understood on flat spacetime. And today there's a fair question to be asked whether one can develop alternate methods to understand the asymptotic behavior of these higher spin fields. And one of these specific methods which has been used along for understanding Maxwell equation in particular, with some success for instance, by Peter and Lars, is the use of symmetries of the spacetime. And one way the use of symmetry of the spacetime has been used is as follows. So maybe you have noticed it, but from symmetry, something that Lars have said, from symmetries of the spacetime, you can go to symmetries of the space of solution that you're having. More specifically, if you start by phi, which is a Maxwell field, using this kind of symmetry, you have some P, which is an operator, a differential operator. And like this, you produce a new field, psi, which satisfies also the Maxwell equation. So from the symmetry which is existing on the space-time, you are constructing a differential operator which will transform Maxwell field into Maxwell fields. And this has been used, for instance, to make some kind of energy estimates. Now when you look at these things here, you can think at the original Maxwell field phi as being a potential of some kind for the Maxwell field psi. Okay? And this idea of exploiting both the symmetry of the space-time and reducing somehow has been used already in the context of Hertz potential. And this structure, more specifically, in the context of Hertz potential. So I won't talk about it in much details. You will have a grasp of the meaning of this maybe tomorrow during Thomas' talk, where you'll have maybe an idea of how second-order symmetry operators can look like potential of some kinds. But what is interesting with respect to this potential is first that you exploit the symmetry of the space-time as much as you can, and second, in the specific case of the Debye potential here, you can try to reduce your complicated field to one scalar field. Okay, complex scalar field. Now, how can we use this how this idea of Hertz potential has been used when we're thinking of decay, studying the decay of a higher spin field. Yes, it doesn't work. Yes, this idea of using Hertz potential to study the asymptotic behavior of higher spin fields has been used by Penrose in his paper on the peeling of fields. More specifically, Penrose was studying higher spin fields, so spin S fields, and for these spin S fields, he has constructed some kind of potential of order 2s, meaning that here you have 2s derivatives. And this potential here is satisfying a wave equation of some kind. And from a decay ansatz that is making on the solution of the wave equation is deducing the asymptotic behavior of this higher spin field psi. This representation by a potential which is calling this a Hertz potential is only a priori in his paper local representation with a complex scalar. Okay, so this is a nice picture where we can at least link Hertz potential and the decay of asymptotic and the decay of higher spin fields. Now, if we start thinking at this on a curved background, and especially why not the curved background, this has been studied in a very specific way, especially by Cohen and Kegeles in '76, for instance, but there's a lot of literature like this. And this has already been mentioned, that there's a possibility to generate from solution of the wave equation, solution of the Maxwell equation. So if you take G, a two form, which satisfy a wave equation of this type, then obviously this thing here also satisfies the Maxwell equations. Maxwell equations which are and the particularity of this Maxwell equation that we are generating, so there's a bar here because this is a space-time, so this is in dimension 3+1. So just for the notation. And the particularity of this solution here, it's uncharged. In the sense that, so Lars has introduced this notion of charge. So you can compute something like this on the Kerr black holes. So you take a two sphere that is going around the axis. You have a two sphere like this. And this will be non-vanishing, and see, this can be thought as being a charge for your Maxwell field. And the particularity of these charges is that they are generating of the solution of the Maxwell equation, which are not decaying. So static solution. Static solution and decay does not go together. We don't like this. So what we would like to do is to have a decomposition of any Maxwell field into something which will be generated by the Coulomb solution, plus something which will be integrated, represented as a Hertz potential. So algebraically speaking, what is happening, I guess it's almost clear for everyone except me. And the hope really is that this thing here will radiate, decay the way you want about it. The thing any estimate that you want will hold for this thing here, under suitable assumption. So now that I have given these hopes, let's say immediately that we have to, for the duration of this talk, forget about them. So this high D, the purpose of this talk is the following. We just want to understand, in the most simplest case, what we can do with this Hertz potential to study the decay of higher spin fields. Okay? And to understand this, let's take a problem which is simple. Problem which is simple mean flat space-time. The result which is stated in the paper that I've talked about before, all for arbitrary spin. But for these talks, because I know that you don't like Penrose notation, I will talk only about spin 1 and spin 2 fields. So spin 1, Maxwell field and linearized gravity. And the purpose of this talk is I'm giving myself a solution of the Cauchy problem. And I want to construct a potential, a Hertz potential, by constructing initial data for this Hertz potential which satisfy wave equation. Okay? And I want to have a nice, complete description of the asymptotic behavior of my Hertz potential. And the important thing is, here, there's a preliminary result of Christodoulou-Kleinemann for this field, Maxwell and linearized gravity, so we have something to compare with. Okay, when did I start? Just to be certain? 47. Great. So, the first thing I need to talk about is how wave equation decays. This is something that you must all know, but since I was not certain that I know this myself, I need to talk about it in a bit of detail here. The second thing is I will explain how you can construct potentials from in the right context of the Cauchy problem. And the last thing I want to talk about is the nice description that we have from this representation with potential for higher spin fields, meaning here Maxwell in linearized gravity to make things readable. So, as I say, we have a simple problem. This simple problem is Minkowski space with a wave equation. So I'm considering a nice Cauchy problem here. And I will look at a nice Cauchy problem with this kind of data in weighted Sobolev spaces. So the only thing that you need to know about these Sobolev spaces is the following. If you take F, which is in HK sigma of R3, and you take K bigger than 2, then you know that F of X will behave like this when X goes to plus infinity. Okay? This is the only thing that you need to know about these Sobolev spaces. This kind of notation are, for those who are familiar, I'm working with Bartnik notation, not with McEwen notations. Okay, so I'm working with data which are decaying with this specific decay here. Okay? So this is for the F, for the initial data, and this is for the time derivative, which decays one faster. Okay, and the purpose is to describe how this field decays. This field decay. Right, anyway. So, strangely enough, the result for this kind of thing is not as extensive as we could think it is. So you all know the method of the energy estimates of Kleinemann. With the energy estimate with Kleinemann, you are working with vector fields, and you are saturating your standard H1 norm with this vector field. And this vector field have a very specific weight in front of it. And so this specific weight will correspond to sigma equal minus 3/2, and it gives nice decay result I will present in a minute. You know also aware of the conformal compactification method, which will give decay corresponding compatible with sigma equal minus 2. I'm cheating a little bit because you may need a little more on your initial data, but that's another thing. And apart from these two things which are well known, the result for arbitrary weights is, to my knowledge, and I'm looking for reference, so if somebody has references, I'd be happy to have them. There's not much literature regarding the decay for arbitrary weight. So you've got a result by Asakura in '86. And the best result I'm aware of regarding both decay and regularity is the one from Dankona, Georgiev, and Kubo. And you have a result by Spack in 2008 relying, and Asakura and Spack are both relying on integral representation. So as I said, let's be clear about what I mean by decay and how the field decays. The thing that you have to be aware of is that you have two types of asymptotic behavior. So I'm doing half a conformal diagram. Of course, you won't see anything if I'm doing so. Okay, and I will look at two regions. So there will be the first region, which I will call the exterior region, and second region, which I will call the interior region. The exterior region has to be thought of being the extremities of null rays, containing all the extremities of null rays, and the interior region has to be thought of containing all the extremities of time-like light ray, time-like lines, okay? And how does this decay result works in the method of Kleinemann? So you take initial data which lies in this space with S not bigger than 2. And when you are in the interior region, you decay exactly at the same rate as the initial data, which is reasonable. This is this result here. Now, when you are in the exterior region and you look at what is happening, so I'm introducing, as always, the advanced and retarded coordinates. When you work with u equal constant, which looks like this, you have a decay like 1 over v. Okay? So this is u equal constant. And now when you move along scri plus, you have a weight appearing, which is the weight being this u to the 1/2. Okay? Now, if I'm start differentiating this, the more I'm differentiating in the interior region, the more decay I'm getting. Normal. Now, in the exterior region, what is happening? To understand this, we have to make distinction between the derivatives you're taking. You have two kinds of derivatives. You have the derivative du and the derivative dv. So, and two derivatives which correspond to the angular derivatives. So du is like this. So it's tangent to square plus and normal to the u equal constant. Not normal. Transverse to the u equal constant. dv is tangent to u equal constant and transverse to the surfaces v equal constant, which are like this. Okay? So the more derivative I'm taking in v or on the derivative on the sphere, meaning the more I'm taking derivatives which are tangent to the u equal constant, the more decay I'm getting in the null direction. Okay? The more decay I'm taking in the du direction here, so along the light cone like this, the more decay, the more weight I'm getting in u. Okay? Just to be certain, you take this expression here and you differentiate it. You take this expression here and you differentiate it and give you the result you expect. Okay, so now what can we say about arbitrary weight? The purpose here is to construct potentials. So I won't be subtle about the all I'm interested in is the decay result. Okay, this method works. That's the only thing that matters here. So for arbitrary weight, you take initial data which are in this space. I know that if I'm taking enough regularity, so 3 derivatives, which is a lot, I'm having these two inequality at the level of the initial data. I have an integral representation. I'm plugging this inequality in the integral representation for the solution of the wave equation. And I'm ending up with this kind of, let's call it a kernel, this kind of integral here, which I have to compute, something stupid. If I'm doing so, it happens that I'm having an explicit expression for this thing. So I'm it's not very interesting to have a look in detail at this expression now. The thing is you have two different weights for the function f and for the function g corresponding to phi at 0 and dt phi at 0. So you have to combine g sigma and g sigma minus 1, and so you have a discussion arising on sigma equal the weight equal minus 1. Okay, and I'm also interested in getting the result for all derivatives, and for this you use the standard properties of a certain number of vector fields that commute well with the box. Okay, so something very standard. And if I'm doing so, what is the decay result that I'm getting? Lot of regularity. I'm not denying it. Once again, this is not the point. And then what is happening? So let's take for a moment k, l, and m equal to 0. If the weight is smaller than minus 1, I'm having exactly the same feature as Kleinemann had, meaning I am having a weight of the form 1 plus sigma v to the minus 1. If the weight is bigger than minus 1, I'm just having some decay like v to the sigma. And if the weight is equal to minus 1, we know that we have a log term, which is this log term here. Okay, now when I'm starting differentiating this thing, I'm having exactly the same feature as when I'm looking at Kleinemann result here. So the more differentiation I'm making in V or on the sphere, the more weight in V I'm getting. The more I'm differentiating in U, the more weight I'm getting in U. But this inequality will arise only in very specific circumstances. This inequality has to be satisfied. So somehow I should differentiate enough so that this holds. Okay? So that this inequality is satisfied. If I'm not differentiating enough here, I don't have this behavior described here. Okay? So this thing is a bit important. In the following, it will explain why, it will explain in detail why peeling holds or not, which is something which has been discussed without being clearly answered. And with this small decay result, I can answer it. OK, so now that we more or less know how wave equation decay, the solution of the wave equation decays, we can have a look at the problem of Hertz potential. So this is the only place where there's a spin-off component, almost the only place. So the Hertz potential, the way Penrose was thinking at it, is as follows. You take a spin-S field, which satisfies some kind of Dirac equation. And you construct a potential of order 2s, psi, which satisfies a wave equation as well. And what we want to do is, for a given phi, contract this psi. More specifically, what we really want to do is the following. This is a bad idea. This is too late. We want to start with a Cauchy problem, let's say, for the Maxwell field. And we want, for this Maxwell field, to construct a potential if we can. So we want to construct a potential which satisfies a wave equation. And G at t equals 0 will belong in some space. So, and dtg at t equals 0 will also belong in some space, which is this one. So I'm starting from this. I want to construct this. I'm thinking Cauchy problem. So I'm starting from initial data, and I want to construct initial data. OK? And of course, at the end of the day, what is happening? If I'm constructing the initial data such that when I'm looking at this, if I'm constructing my initial data for my potential so that when I'm restricting the potential equation at t equals 0, this equation holds, by uniqueness, I know that I will have my representation. OK? So here, what I'm about to explain is Maxwell and linearized gravity. And the method I will use are basically Bartnik paper on elliptic series or something simple. So let's have a look. Let's have a look at Maxwell. So Maxwell equation, I guess you are all familiar with this Maxwell equation. You consider Faraday tensor, which is a screw symmetric two-form. If you are giving yourself a unit time-like vector, you can define an electric field here and a magnetic field B. So here, the star is a Hodge duo. And the Maxwell equation can be written df bar, delta bar f. So the d bar and delta bar just means space-time. So 3 plus 1. In a minute, there will be no bar because I will be on space-like slice. And the Maxwell equation can also be rewritten in this way. OK? So more specifically, what I'm interested in, this thing here is a hyperbolic system with 6 real unknowns. I'm looking at data which live in this space here. And I know that the electric field and magnetic field have to satisfy constraints on the t equals 0 time slice. Here, d. And the d here is just the covariant derivative that you have on the t equals 0 time slice. So this is equations which are purely spatial. And I want to construct this potential here the way I've said it. OK? So first thing I have to do, I'm assuming this holds. Now I will restrict this equation at the slice t equals 0. So here I'm having my E and my B. Here I have also two forms. I have a solution for the initial data and the time derivative as well. So here I have to consider not only do I have to consider the electric and magnetic field of the initial data for G, but also for dtg, which I'm denoting brutally dth and dtk. Okay? So I'm having my electric and magnetic field for my two form, which satisfies the wave equation, as well for the time derivative at t equals 0. And now if I'm looking at my equation, this equation here, and I'm making a calculation by restricting it to the t equals 0 time slice, I'm getting this set of equation, which is a link between the EB and the electric and magnetic field of my two form, as well as the electric and magnetic field of my two form at t equals 0. This sounds very complicated. So since for my initial data here, I'm more or less free to choose it the way I want, I'm throwing it this away. Okay? Brutally. Somebody asked me about a question about gauge choice here. This may be the only gauge choice I'm making here. Okay, so now I will assume for a minute that EB belongs to the image of the Laplacian, which means that I have pre-image H tilde, K tilde, which lives in this space, in the Sobolev space I'm looking at. Okay? But the assumption I'm making here is that EB and the image of the Laplacian. Okay, now I'm looking at the geometric constraints. So I'm having, So I'm having delta E equals 0, and simultaneously I'm having E, which is delta D plus D delta. I don't remember, I think I've denoted this H tilde. If I'm applying delta here, I'm killing this part, okay? Remains delta D delta of H tilde, but delta D delta of H tilde can be transformed of delta D plus D delta of delta H tilde, okay? So this is vanishing as well using the constraint equation. Now, if the decay is appropriate, then this implies that E is in the image of delta. This implies that I can kill off this part here. And if I can kill off this part here, actually E is in the image of delta. Well, eventually plus something if the rate is not appropriate, but we don't care about the something. So basically, I solved the equation that I had at the beginning. Good. I'm doing exactly the same thing for delta B. So I will prove that delta B belongs the same way in the image of delta with the right decay. Now, I'm taking initial data for my potential being this, and I'm done, basically. Okay? So the condition so far to admit a potential is to be orthogonal to the kernel of delta in the dual space. So again, something relatively simple. And now there's a small lemma that if you are in this space, actually you can modify your initial data so that you actually L2 orthogonal to the dual space. This is just a purely technical lemma by projection and rescaling. This is something bit boring to do something like this, but it works. So at the end of the day, we are really, for our initial data, in the image of delta the way we are expecting it, in the right Sobolev spaces that we wanted. So the proposition is the following. If you have a weight which is not exceptional so that you have your elliptic series that works correctly, you can take your initial data E naught, B naught for your Maxwell field here. Then you can construct two initial data, G naught, G1, which is living in the right space. Using standard elliptic theory, you are controlling the initial data for your field, for your potential, by the initial data for your field. And uniqueness of the Cauchy problem, you know that your field is represented in this way. Okay? And as I say, if you start with data which is in this space, your initial data are in this space, which is something I want to control. We want to control the decay. Okay, now if you have the bad idea to do exactly the same thing for higher spin field, the picture change barely. So higher spin field, I'm looking at this kind of equation here. So I'm having W, A, B, C, D, which satisfies the symmetry of the Weil spinner. I'm having this equation here. I'm taking initial data. Exactly in the same way for Maxwell equation, I can define electric and magnetic part of my Weil spinner, my Weil tensor. This electric and magnetic part both satisfy constraint equation of this nature. As you know as well, it's a hyperbolic system of order 1 with 10 unknowns. And we want to construct a potential, which I can't write in tensor notation. This is way too complicated. But basically, I want to get W, my field here, as a first order potential psi. So I understand that the intermediary potential are known, Langsos potential, Bergman potential. I have no idea to what they correspond to, but I just wanted to mention this. So in spinor, for those who like spinor, you have a totally symmetric spinor. You have your Cauchy problem, which is a Dirac equation, with your initial data, which satisfies this constraint equation. Okay? Here, this is a hyperbolic system with 5 complex unknown, and the nice potential equation is this one. Okay. So the funny thing here is the procedure to integrate our field is exactly the same, except that we have to change the Laplacian into the Laplacian square. And the thing that will change a lot is the integrability condition on EAB and BAB. So here, to be clear, I'm having my what is the notation I'm using? I'm having my psi, which appears as a fourth order derivative of something j. I'm looking at what is happening at t equals 0. So this is some operator which I'm denoting by r, which will depend on g plus something, no, sorry, gradient g plus something dtj. Okay? So this is an equation I have to solve. This r here will appear to be a third order operator. And I know that my field here satisfies the constraint equation here. Hopefully, as in the Maxwell case, the constraint equation I'm having here will guarantee the existence of a preimage by the operator I'm having here, R. And it happens to be the case. So if I'm looking at the constraint equation I'm having here, so this is a kind of divergence onto onto tensors, then this equation here, if EAB satisfies this constraint, then this equation here, with this part disappearing, so this I don't want, admits a solution. And this R here is actually a well-known quantity because this is a linearized Coton-York tensor. So why do we have this strange picture here? So these things actually have been studied, let's say in the 80s, as far as I'm aware of, maybe in other contexts, but this is a context I know. And it has been studied here in Grenoble, actually, by one of the vice presidents of the university, if I'm not wrong, when they were studying conformal rigidity of a metric. So what is conformal rigidity of a metric? You take one given metric, G0, and you are considering a family of metric GT, which is more or less conformally rigid with respect to your initial metric G0. If you have a family of diffeomorphism, okay, you apply your family of diffeomorphism to your metric G0, you get a family of metric GT modulo a conformal factor, which depends on T. So you take this initial condition to start this. Now, if you look at the derivative of this at T equals 0, you obtain some kind of constraint equation. And the constraint equation that you're getting are the following. So X is the thing, your vector field that will generate your family of diffeomorphism, and H will correspond to the derivative of your metric GT. And this equation that you are seeing on the left-hand side, this operator you're seeing on the left-hand side is a well-known operator. This is a conformal killing equation with a metric here, with two tensor here, which can be written in spatial spinor in this way. So here, I'm reminding you that the unknown is x, what is given is h, okay? And this equation here can be integrated only if this h satisfies some constraints. And these constraints are providing by this linearized Cauchy-York tensor. Okay? So, how do we compare this to Maxwell? No, it's not this. Yes, here. So this result, as I said, is due to Gasky and Goldschmidt in the 80s. It has been redemonstrated by Baig 10 years later, well, 13 years later, because the initial paper was written in French. And so if you want to solve this equation here, so delta star f equal omega, with omega which is a one form, okay? So you want to construct a one form f, or, so this is an overdetermined equation, which means that the left-hand side has, the right-hand side has to satisfy some constraints. Or if you want to solve this equation here, again here, the right-hand side has to satisfy some constraint, then these constraints are all described by these two elliptic complexes. So the first complex is more or less a variant of the de Rham equation, and the second complex is here. So here you have one form, here you have TT tensors, traceless two tensors. Here you have your conformal killing operator. You have your linearized Cauchy-York tensor, and you have your two divergence. Okay? So I understand this is well known in some people studying some geometry and yeah.
Are you saying these two equations are equivalent?
No, of course not. No. It's two different equations. These are just a comparison between something that I understand and something I don't understand.
So wait, which one do you understand?
Well, it's not clear, but I would say the one on the left-hand side.
This is in 3 dimensions.
Yes, this is in yes. So here everything is in 3 dimensions. The result by Gasky-Goldschmidt hold in higher dimension, but this is a totally different tensor. Why? So the Cauchy-York tensor, if you consider conformal flatness in dimension 3, the Cauchy-York tensor will be the one that will tell you about the conformal flatness of the manifold you are looking at. Yes. This is in 3 dimensions. Yes. Okay. So, small comment about this conformal flatness. Now, if you are looking at all the equations we have been looking at so far, are invariant, which are conformally equations which are conformally invariant. Our potential business is almost conformally invariant as well. So it's not completely surprising that we end up with studying these kind of things at the end of the day, okay? For when we want to construct potential. Okay. So at the end of the day, we have a completely similar result for higher spin fields. So as long as your weight is not exceptional, with a lot, so I'm taking S not bigger than 3, but here this is really not needed. I can, if I'm considering initial data which satisfies the constraint equation in these Sobolev spaces, I can construct initial data which lives in this space here. I can control the initial data here by the initial data of my potential, and I'm having, using uniqueness of the Cauchy problem, this nice representation. And Xi satisfy a wave equation. So this kind of result I've presented to you, I've presented in spin 1 and spin 2 because I can write everything in tensors. Just to be specific, it's all for arbitrary spin. We have this kind of construction for arbitrary spin. We barely don't make difference between half integer or integer spin. This runs quite smoothly. So now we are coming to the part that we wanted to answer at the very beginning. We want to study the asymptotic behavior of the kind of equation that I've written. So hopefully one day, well, it's clear for Maxwell, for spin 2 fields, God knows, but literally. Hopefully it will be extended in one way or the other to K spacetime. I will make a list of abstraction. It's very long. And we have something to compare with, which is the work of Christodoulou-Kleinemann for very specific weight. And here we want to derive exactly the same kind of decay as here, using a representation of field using potentials, okay? By reducing this tensor equation to a scalar wave equation, as long as we're in flat space-time, we don't have that much problem to reduce things to scalar wave equation. Okay, so I'm not making any kind of proof here. I will do just numerology. So, numerology. Now, I'm just making consider specific weight, but the result again will hold for all spin and all weight, non-exceptional, so that we have a representation with potential, but this is really not an issue here. So, if we look, for instance, at the case of the weight of the initial data for Maxwell equation is in -7.5. The potential will lie in -3.5, okay, making two jumps. The interior decay will be t to the -7.5, which is not surprising for something which is hyperbolic, which is a geometric equation. We have exactly the same decay as the initial data. Now, I have to be a bit more careful about the decay for the components of the field. So in this business, everyone is using its own notation. So you all have your favorite notation in the list. If you don't have, please let me know at the end. So the first thing you can consider is I will have to have a look at the restriction on my field in the null direction. Okay, this is what I want to do at the end of the day. Null direction will mean in the direction du or in the direction dv or in the null direction between brackets which are tangent to the sphere here. Okay? So this null direction have different notation. So you can look at the restriction on f contracting with du and direction tangent to the sphere. You can look at f contracting with dv and du, or f contracted with only the direction tangent to the sphere. And you can look at f contracted with dv in this direction and the derivative tangent to the sphere. You have all these zoology notations. So the alpha bar, I think this is Christodoulou-Kleinemann. The phi -1, this is Peter coming from Price, am I wrong? This is Peter coming from Price. And phi 2, this is Penrose. Okay? So now if you look at the decay result that I've stated at the beginning, I have my field here, f, delta dj. So here I have two derivatives. And there's three situations that can happen. I can have either I'm having du duj, or I'm having du dvj, or I'm having dv dvj. Okay? And if you look at the theorem of Kleinemann here, accordingly to the different derivatives I'm taking, I'm having different behavior. Okay? So the more derivative I'm taking in u here, in the u equal constant direction, the less decay I'm having. The more decay I'm taking in the direction v here, or in direction on the sphere, the more decay I'm having in the v direction. So just in the u equal constant. Sorry. So just to remind you, I assume that you don't see what I'm doing. Hop. So you have your u equal constant. Yeah. You have your v equal constant. And you have your du and your dv. Okay? So the more derivative I'm taking in the direction v, so outgoing direction, the more decay I'm getting. The more taking direction in direction u, the less decay in the direction u equal constant I'm getting. So how does it translate here? Hop. Here, at this level, I'm having the less decay possible. U to the minus 5 half, V to the minus 1. Here, when I'm looking at this component here, so here there's a typo. I'm deeply sorry. This is a minus 3 half. So this is U to the minus 3 half, V to the minus 2. And if I'm looking at the last component whose all components are outgoing, F dV ES2, I'm getting the more decay V to the minus 3. OK. So now if you want to compare with the result by Kleinerman, there's something peculiar rising where at the end here, for the last component, the faster decaying component, I'm having a loss at the minus 5 half. So there has been some business about discussing where this loss is coming from. Everyone knows that it's coming from the nature of the initial data. I think it's clear, but this answer clearly, we will answer with this method clearly what happens here. So we have, the good thing is at least we have the same result as Christodoulou-Kleinerman, so it seems to work. So now just to let you understand what is happening here, in Christodoulou-Kleinerman, you have sigma, which is for the initial data, which is minus 5 half, which correspond for sigma, which is minus 1 half, which is above the critical weight minus 1. Okay, so when I'm looking at this component here, I'm still having sigma smaller than minus 1, bigger than minus 1. And so this is why I have to resort to the formula that here, I will decay like V to the minus 1 half minus 2, which gives us minus 5 half. Okay? So this is clearly coming from the fact that we don't have enough decay at the level of the wave equation to understand the decay of higher spin field. Okay, now if you want to do this for higher spin fields, you can, of course, do it. So if you look for all weight in the interior region, so here I'm making interior region, exterior region, but it's really not, it doesn't matter, okay? This is global. So, but in the interior region, if you decay like 1 to the, like T to the sigma, like R to the sigma at the level of the initial data, you get exactly the same amount of decay in the time direction. For the weight, sigma equal minus 11 half, I have to comment about this weight afterwards. You get a very nice decomposition of your of the null component you look when you're looking at your field, phi I. So this phi I as a null component, you're looking at your field exactly in the similar way I've done. It's exactly the same kind of decomposition I've done here. Now for the weight 7 sigma equals 7 half, you're getting this decay here. You have a failing at distinguishing the last two components, which is coming exactly from the same phenomenon as described here. I have described here. And this is exactly, once again, this agrees with the result by Kleinerman, so we are safe. By Christodoulou and Kleinerman, so we are safe. So here, about this weight here, sigma equal minus 1 half, just a small comment about conformal compactification and asymptotic behavior. So when you are working with data which are generate, when you're looking at data for which you can define some kind of continuity at scribe plus for the conformal rescaling, just by unraveling the conformal compactification, you get some decay. This decay for higher spin field will correspond to minus 2s minus 2, so minus 10 for higher spin field. So when you are below this threshold, we know that we have peeling, okay? And here we have peeling. Nonetheless, there's something a bit peculiar which arises. So when you are between minus 10 and minus 9, you apparently don't have a nice conformal picture, but nonetheless you have peeling. This is just a small comment. So this funny thing with this method here, at least it answers quite clearly about when the peeling phenomenon arises or not, and it's a fine understanding of this thing, which is more or less satisfactory. Okay. So I'm reaching my conclusion now. So at least we are happy it works. It works quite smoothly. We don't have many difference for different spin, for different weight. We are more or less happy. Of course, we are all thinking at Kerr stability. This is complicated. This you know better than me. And the interesting thing why we want to try to carry on with this Hertz potential method is that we know that these Maxwell fields are not charged, and this is something we are happy with, and we would like, it would be interesting nonetheless to make sense to something like this and use this structure to prove some kind of decay. Okay, this would be some kind of very vague idea of, I think the word scalarization has been used several times. If we want to study higher spin field to something which will be potential, which can, if we can, restrict to one scala, it would be great. If it's true or not is another question, but it would be at least a very nice structure. So far, this is the motivation of the method that I'm recalling. The problem is whenever you're going to curve space-time, you are more or less missing absolutely everything. An elliptic series that you are happy with, differential complexes, well, at the level of Maxwell equation, we don't have a problem. When you want to go to higher spin fields, the question is not relevant in any case because the consistency of your equation can be discussed. But ideally, the right thing to understand this problem in the most nicest way you can think of is to make a Hodge-Helmholtz decomposition on non-compact manifold with boundary for weighted Sobolev spaces. Good luck with it. It's not clear to me regarding the existing literature about this is not clear. So this is a huge piece of work which has to be done. There's nonetheless some direction in which you can say something. There's something that I keep mentioning at the very beginning which is interesting and that you are more or less seen in Lars's talk, in Lars's course, which is try to reduce this potential to one scalar potential, which is called a Debye potential. Okay? This is something that you can try to see, and try to see whether to use this result at the level of scalar wave equation, prove some kind of estimate like this, and hopefully try to derive something from Maxwell. This is completely crazy, but whatever, we can think at doing something like this. And the thing that we can, on K spacetime, that makes us think that we can do something about it, and I guess it will be clearer in tomorrow's talk, what kind of things you can play with in K spacetime, is the existence of a killing spinner that will allow some kind of reduction from Maxwell equation to some kind of scalar equation, or from Maxwell equation, well, yes. And this killing spinner, which generate both symmetries among solution and the potential, I think is something we have to dig in if you want to carry on understanding this business of potential for higher spin fields. Okay, I will stop here. Thanks.